Welcome back, everybody. We are now in the cardiovascular system and dealing with the blood vessels. And this is the tail or the last section of the cardiovascular system. We've dealt with the blood, we've dealt with the heart. So now we're going to find out how the blood vessels are uh, playing a role in the transport system of the heart. So blood vessels will be the delivery system. It's a dynamic structure and would begin at the heart and would end at the heart. So they are following a closed circulatory pathway. They also work with the lymphatic system to circulate fluids. And there are three different types of blood vessels. You have the arteries, the capillaries, and the veins. The capillaries carry blood away from the heart and they carry oxygenated blood except for the pulmonary circulation, that's the exception to the rule, which carries oxygen poor blood. The arterial uh, pulmonary arterial the pulmonary arteries are delivering blood going towards the lungs and therefore would still be carrying oxygen poor blood, and of course also the umbilical vessel of the fetus. The capillaries, on the other hand, would connect the arteries and the veins. They are in direct contact with the tissues. They directly serve the cellular needs of the body. So this is actually that feeds into the tissues themselves. The veins carry blood toward the heart. The blood is obviously deoxygenated or oxygen poor, except for pulmonary circulation and the circulation on the umbilical vessels of the fetus. So here is a picture of the it's a diagram of the entire blood vessel of the human body, and the three different types would be, first of all, the one that delivers blood going towards the heart will be your veins, and then once in the heart they are delivered to the lungs, and then they go back to the left side of the heart, and this time they're already like oxygen rich, and the arteries carry the oxygen rich blood, and in between them is actually connecting them will be your capillaries. And of course, take a look at how or what the relationship is of the lymphatic system to the circulation itself. The lymphatic system pulls all excess tissue fluid, and the excess tissue fluid are coming from the tissues. When a capillary leaks out the tissue fluid, whenever we are, well, in most cases, whenever we are slowing down or whenever we are sleeping, okay, and the tissues get pretty much a lot of the fluid. It doesn't stay much in the blood vessels because of the slowdown in circulation, and so it doesn't have to stay in the tissues because it will have to be drained from the tissues by the lymphatic system and will be brought back to the subclavian vein, back into circulation. So we have three different types blood vessels, and all vessels consist of, just like the way the name says, it is a vessel. So it would have a lumen, a central blood containing space surrounded by a wall. And the wall of all vessels except the capillaries have three layers: the tunica intima, the tunica media, and the tunica externa. The capillary on the other side would be made up only of one layer of cells, and its endothelium is actually made up of has actually a sparse basal lamina. And so, this is a good picture showing us the one of the layer. This is actually your tunica intima, the innermost layer, which is in intimate contact with the blood. And therefore, this is the tunica intima, and that's the tunica intima. And basically, the tunica intima of the artery and the vein doesn't really differ much. They're made up of simple squamous epithelium, and lines the lumen of all blood vessels. It is continuous with the endocardium, okay, and it would have a very slick surface, non-wettable surface, and that would reduce friction, and that would reduce platelet aggregation. I think that thing should be avoided. And there is actually a subendothelial layer, and the subendothelial layer, that's your subendothelial layer right there. The vein have thicker subendothelial layer, and the artery would have a thinner subendothelial layer. This is a layer of connective tissue, basement membrane, and they are found only in vessels that are larger than 1 millimeter. And you have the tunica media. The tunica media is the middle layer for both of them. The middle layer is composed mostly of smooth muscles, and that is actually your smooth muscle layer, that red or heavy or dark pink area, and made up mostly of sheets of elastin. So you have, what do you call this, in the artery, two layers of elastin. You have an internal elastic membrane, and you have also an external elastic membrane. The smooth muscle, the tunica media, is sandwiched between the internal as well as the external elastic membrane. Now, the sympathetic vasomotor nerve fiber innervates this layer. It controls the movement of the vessel, like vasoconstriction. Okay, well, the lumen's diameter is decreased, or vasodilation, which is actually increasing the lumen of the diameter of the lumen, and pretty much this plays a major role in blood pressure. So the bulkiest layer that is responsible for maintaining blood flow and blood pressure, because of this, most especially because of this vasoconstriction and vasodilation, is actually the tunica media, and now most especially in the arteries. And you have the tunica externa. The tunica externa, the outermost layer of the wall, is also known as the tunica adventitia. It's composed mainly of loose collagen fiber. This is actually your tunica externa in the vein, and in the artery, that's also the tunica externa, made up mostly of loose collagen fibers that protect and reinforce the wall and anchors it to the surrounding tissues. They are infiltrated with lots of nerve fibers and lymphatic vessel. The large veins also contain elastic fibers, okay, in this layer, but very, very little. And you have in large veins what you call the vasa vasorum. These are a system of tiny blood vessels that is found in larger vessels. So the vasa vasorum is the blood vessel that is feeding the large vessel. So even if your large vessel is carrying blood, it would still need to be fed because of the thickness of its wall. And you have right here pretty much an illustration, a summary of blood vessel anatomy, showing us that the artery is pretty much, these are all arteries, okay? And among all the arteries, you have the thickest artery, which is the elastic artery. And then you have the muscular artery, which will have a good amount of muscle relative to its size and relative to its elasticity. The muscular artery has lots of muscles, and the elastic artery would have more elastic fibers than the muscular artery. And this is your arterial with very little smooth muscles around it, and pretty much the diameter of the arterial is also very small. Right here, the diameter of this is about 1.5 centimeter. This is about 6 millimeters, and this one is about 37 micrometer. So, and here you have the capillary, which is about, well, 9 microns in diameter. The veins, which is about 20 microns. And then the veins, this is a venule. The big veins is about 5 millimeter. Could just see the differences in their sizes. And right here is a good picture, which is going to tell us comparatively the difference between a vein and an artery in terms of anatomy. Okay, I am going to leave this to you. You will have a chance really to work closely with this one, most especially if you're going to work on it also in your textbook. So let's start individually taking up all of these little blood vessels. This will help you more in your lab. Arteries are divided into three groups based on their size and their function. You have your elastic artery. This is your elastic artery. Then you have your muscular artery right there in the middle. You can see the difference between them. And then you have your arterial. This is actually a gross enlargement of the arterial, and the arterial is not as big as an elastic artery, and so would be your muscular artery. So they are not really good representations in terms of size. Elastic arteries, this is your elastic arteries. They are very thick walled with very large, low resistant lumen. An example of this is your aorta and the major branches, also known as the conducting arteries, because they conduct blood from the heart to the medium-sized vessels. Elastin is elastin is actually that yellow part. Okay, they are found in all three layers of the elastic arteries, most especially in the tunica media. They contain a large amount of smooth muscle, but they are not uh, active in vasoconstriction. So they are not involved in controlling the blood vessel by vasoconstriction and vasodilation. Your elastic arteries act as pressure reservoir, and they expand and recoil as blood is actually ejected from the heart. The elastic arteries, when they harden because of age, you will have a situation or a condition that will be called arteriosclerosis. And this will be the time when each time the heart would pump and would deliver much pressure, it will not anymore expand. Okay, and the movement of expansion and recoiling would be very minimal, and that's the reason why uh, people who would have this hardened arteries, we call it, would have also hypertension, and that's because of arteriosclerosis. Now, elastic arteries give rise to the next one, which is your muscular arteries. I have a picture here of the muscular artery. This is also known as the distributing arteries because they deliver blood to the body organs. The diameters of the distributing arteries run from the pinky finger size to about pencil lead size. They account for most of the named arteries that you're going to be accountable for in your lab, and they have the thickest of the tunica media and more smooth muscles, but less elastic tissue than the big arteries. The tunica media is just like what I mentioned before, sandwiched between the elastic membranes. These muscular arteries are very active in maintaining the blood pressure because they're active. They're actively engaged in doing vasoconstriction if it's needed. Arterioles, the smallest of the artery, pretty much they are the larger ones would be made up of three layers. They would still have the tunica intima, tunica media, and tunica externa. But the smaller arterioles, as they get smaller and smaller, are mostly single layer of smooth muscle surrounded by endothelial cells. They control the flow into the capillary beds, okay, and they're also known to be the resistance arteries because the changing diameters would change the resistance to blood flow. And these arterioles eventually lead into the capillary beds. So now we have a capillary, the smallest of the blood vessels. Take note that the capillaries is made up only of one single cell that is actually folded. So this is your single cell. This red thing is a single cell. You see the nucleus right there? It's a flat cell and it folds into itself. And the lumen of that folded cell is the lumen of the capillary. You could just see how tiny this is. They are microscopic blood vessels. They're only so small that only one red blood cell can pass through at the time. The walls are just thin tunica intima, okay, which is the endothelial the endothelium almost, okay. In the smallest vessel, one cell pretty much forms the entire circumference, just like what I tell you. And then they have some specialized cells which you call pericytes. In this picture here, the blue thing that looks like flowers are the pericytes. They are spider-shaped stem cells. They help stabilize capillary walls. They control the permeability and they play a role in vessel repair. They actually are stem cells and they can differentiate into new capillary cells if the capillary become we call it if they are pretty much like injured or destroyed. They supply almost every cell except for cartilage. So your capillaries are found almost in every cell except for cartilage cells, which is avascular. Okay, the epithelium also, and then cornea and the lens of the eye. These are the only areas in the body that do not have uh, vascularization, and therefore you do not have any capillaries in it. Remember this in your exam, it will come. Cartilage, epithelia, cornea, and the lens of the eyes are the only places that would not have capillaries. So what is the function of your capillary? Well, your capillary is dealing with exchange of gases, nutrients, waste, hormones, etc., between the blood and the interstitial tissue. So you have the blood right here, and you have your interstitial tissue right there. So there is an exchange of gases right here and nutrients, okay? And then that is this portion right here is the portion of the capillary that would be high in oxygen. It is now by delivering oxygen just by way of diffusion into the tissue and nutrients into the tissue. And that part, okay, where you have already less oxygen inside, it will now be picking up carbon dioxide and waste, and then back to the heart, and to be going back also to the lungs to pick up to be oxygenated. Okay, and then right through the liver, where it's actually going to pick up a lot of nutrients that has been digested and processed in the liver. So there are three types of capillary. All capillary endothelial cells are joined by junctions, tight junctions with gaps, which you call intercellular clefts. And they allow passage of fluids and small solids. So three types. The first one is your continuous capillary. This is exactly how a continuous capillary would look like. These type of capillaries are abundant in the skin, in the muscles, the lungs, and the central nervous system. The continuous capillaries of the brain, though, are unique, that they form what you call the blood-brain barrier. They're totally enclosed with tight junctions, and there are no intercellular clefts. The next one is what you call the fenestrated. Take a look at the difference between your continuous capillary. Take a look at that and this one here. What's the difference between the two? Take a look at this portion right here where it's actually smooth. On the next picture, now you have something that looks like Swiss cheese. So that's the reason why they're called fenestrated capillary. They're found in areas involved in active filtration, such as the kidneys, the intestine, or in the endocrine glands where hormonal secretion is actually happening. Its endothelial cells contain like those Swiss cheese pores, like cold fenestrations that would allow for increased permeabilities. And the fenestration usually is covered with thin glycoprotein diaphragm. Now, the third one looks like a dilapidated capillary, and this is your sinusoidal capillary. There's very few tight junctions. The fenestrations are usually larger with larger intercellular clefts. There is incomplete basement membrane. That's actually the basement membrane, the almost translucent material, and usually have very large lumens. They're found only on the liver, on the sinusoids of the liver. The bone marrow, the spleen, and the medulla or the middle portion of the adrenal gland. The blood flow here is very sluggish. This would allow time for modification of large molecules and blood cells that pass between blood and tissue, and they contain macrophages also in the lining to capture and destroy foreign invaders. One very typical capillary, typical of this type, is actually the capillaries of your liver. Then now you have your capillary bed. The capillary bed is an interwoven network of capillaries between the arterioles and the venules. This allows microcirculation, the flow of blood through the bed into the arteriole and from the arteriole to the venule. And microcirculation pretty much is happening from the arteriole to the venule. All right. Now there is terminal arterioles. Let's take a look at where the terminal arteriole is. This is your terminal arteriole. They branch off the arteriole that would further branch off into 10 to 20 capillaries. These 20 to 20 capillaries are the exchange vessel that form the capillary bed. This is where exchange of gases, nutrients, and waste from surrounding tissue takes place in capillary. The capillaries will now drain into the post-capillary venule. So, if the arterioles are constricted, like this, is constricted, then no blood flows through the capillary. So, what will happen if the terminal arteriole is constricted and no blood flow is actually going through the capillaries? Does that mean that really blood cannot anymore be received by this venule right here? No. There is actually what you call a thoroughfare channel. Let me see if I have a thoroughfare there, right here. This is actually showing us how, if this particular arteriole is going to be like shut, blood is not going to go through here anymore because it's not anymore going to be delivering blood here. There is actually a thoroughfare channel. The thoroughfare channel allows blood to go through from the arteriole to the venule. This is just like having a heavy traffic from the local right there. But if you go through the main road, okay, you still could reach your point, which is actually the venule. Now, the precapillary sphincter. These are your precapillary sphincters. These are smooth muscle cuffs surrounding its true capillary that branches off a met arteriole. They act as valves regulating blood flow into the capillary beds. They can actually shut down this entire thing. This entire thing gets to be shut down by the precapillary sphincters. But that's the only thing that they can shut down. This main thoroughfare channel remains open, okay, for the blood to go through, even if this part here is going to be shut by the precapillary sphincter. What is the purpose of shutting down? Why would a precapillary sphincter close? Well, pretty much shutting it down allows the movement going through the venule, and even if this thing is going to be emptied out, opening it will pretty much like allow the gush of blood through it. So it stabilizes the flow. It actually creates a pressure for the blood to pass right through the capillary itself. Now, let's take a look at the veins. The veins carry blood toward the heart, and the formation begins when capillary beds unite in the postcapillary venules and merge into larger veins. So, capillary connects to the venule. The venule is actually the baby veins, and they are the point where the oxygen poor blood coming from the capillaries would start to be flowing. So capillaries here unite to form postcapillary venules. So immediately the name of the venule that connects immediately to the capillaries will be called postcapillary venules. They're made up of endothelial and a few pericytes. They're very porous. They allow fluids and white blood cells into the tissues. And the larger venules have one or two layers of smooth muscle, but the little venules have only about one layer. So the veins formed when the venules will converge. They all have the layers, but would have thinner walls with large lumen compared with corresponding arteries. Now, the tunica media, the middle part, is very thin, but the tunica externa of a vein is thick and would contain collagen fiber and elastic network. The large lumen and thin walls make good storage vessels. Matter of fact, you call veins the capacitance vessel. They are actually blood reservoir, and they carry about 65% of our entire blood supply. And here's actually like a very good pie chart showing where you will find the blood in all of the blood vessels. The systemic arterioles would carry only 15%. The pulmonary blood vessels, 12%. Heart has 8% of our total blood volume. Capillaries has only 5%. And where do you find most of our blood? Right there in our veins. So the systemic veins supply all of the body except the lungs. They are very distensible, and because of the absence of elastic or elasticity itself, once you distend them constantly too much, they stay that way, and that's why the those blood vessels that you see right there under your skin, they are only veins. You do not see the arteries because the arteries are deep seated, and the veins are the ones that are located in the periphery, almost very close to the skin. And the veins contain a large proportion of the volume, and that's why they're called a volume of blood. That's why they're called the blood reservoir or the capacitance vessels. So the veins or the blood pressure in the veins are lower than the arteries. So adaptations would ensure the return of blood to the heart. And one of the adaptation is actually your valves. Okay? The venous valves prevent the backflow of blood that is pretty much most abundant in the veins that are found on the limb area. Then you have also venous sinuses. These are flattened or flat veins with extremely thin walls, and they're composed only of the endothelium. And you find the venous sinuses in the coronary sinus of the heart and the dural sinuses of the brain. And you've already studied what the dural sinuses are of the brain when you were in AMP1. Now, and also you've learned also where the coronary sinus is. No, not yet, not yet. But you should have seen the coronary sinus, and you should have already identified it when you took the lab in the heart. Now you're going to see them again. So, and this is an example, a good example. I included this in my slide just to give you an idea of when you're comparing and contrasting an artery and a vein and a capillary right there in the middle. So here is now a summary of all the blood vessels. This is just a continuation of what we did, and I think we had seen this. So let's take a look at the homeostatic imbalance. Varicose veins is very, very common. It's dilated, painful. You could see and ugly due to incompetent, leaky valves. Factors that contribute mainly would be hereditary and conditions that would hinder venous returns. And examples of this will be prolonged standing in one position, and obesity or pregnancy, blood pools in the lower limbs, weakening the valves, and pretty much the valves are, after that, would not be working properly anymore. So right here, you have a comparison between a normal vein with normal valves, okay, and a vein where the valves are not working anymore. When the valves are not working, remember that with the direction of the blood going up, because your heart is right there, okay, in the superior end of your body, and the blood coming from your limb needs to go all the way up. And as it is going up, it by way of gravity, if you're constantly standing up, all of them, the blood the tendency of the blood will be to go back down. But that's going to be prevented because of valve. If the valves are working well, then you know that you're not going to have any problem. However, if the valves are not working, if this particular valve here is not working, then this particular area will be heavy with pressure of the blood and would start to dilate. And so now you could see that this particular abnormal blood vessel have many valves that are not working properly and is causing the dilation, the irregular dilation of the blood vessel, leading to the irregular shape of the blood vessel itself. That's what you call varicose veins. And then another homeostatic imbalance is actually the hemorrhoids. All right. Uh, Elevated venous pressure pretty much can cause varicose veins, and the varicose veins are found right there in the anal canal. Straining, most especially when you're delivering the baby or when during bowel movement, and we do that every day, would raise the intra-abdominal pressure, resulting in varicosities in the anal veins, and then you call that hemorrhoids. There are internal hemorrhoids that could develop around the periphery of the anal canal, and some of them actually can develop outside among the perianal blood vessels. Okay. Anastomosis. Anastomosis is actually the point where two blood vessels would merge. Now, anastomosis, for the most part, among humans, have helped us in delivering blood to the vital organs. And there are many different types of anastomosis. One of them is what you call the arteriovenous shunt. This is where the artery flows directly into a vein. Okay, this is your arteriovenous anastomosis right here. I'm showing them to you now. All right, and then you have your venous anastomosis. The venous anastomosis is actually the anastomosis only found between two veins. Okay, and then arterial anastomosis, who is actually when two large arteries merge and would form collateral circulation like this. Arterial anastomosis is very vital, most especially very vital when the anastomosis is found in vital organs that would probably be threatened by possible blockade. Imagine if this is actually a part of your heart, and if one particular part has been blocked, then you know that there are collateral circulation that could still be feeding that same side on the other side of the block. And imagine if this is also your brain. Okay, your brain, which is actually very vital, cannot lose blood supply. So if in the presence of arterial anastomosis, and there are, and you'll find out that the circle of Willis is a very important case of anastomosis that actually helps circulate blood around the brain. That even when you have, let's say, one block right there, it may not necessarily cause immediately a stroke. Okay, you could still survive. And even with the heart, one block would, because of the if it is actually found in an anastomosis coronary circulation, then you know that there are collateral circulation that would feed the other side of the heart. So